Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hi everyone. My name is Dr. Munzir bin Abdullah. I'm a scientist at the Institute of Nano-Optoelectronics Research and Technology, University Science, Malaysia. So my research is in the field of optics and photonics. And one of the photonic device that I'm interested in is light emitting diodes, or LEDs. I'm sure you have heard about LED before, right? So you can find LED in almost everywhere with you now, in your smartphone, in your laptop, your smartwatch, your tablet, and in your car, and many more. Nowadays, we use light at home and school pretty much all the time, not just during night, and that's burning a lot of energy. If you look at the all electricity generated, when we talk about the power across the world, then actually about a quarter of it is used for lighting. So that's a huge fraction of the world and electricity generation. So a quarter of the world electricity generation just goes into lighting up our homes, our streets, our schools, and all the places we go. Okay, these are some of the application of LEDs, right? So the first one is, of course, to light up our houses, not just during the night, right? But also during the day. On the top right, we have application in the streets, headlamp of your car, public transport, traffic light, so on and so forth. At the bottom left, we use a lot of energy for stage lighting, for entertainment, for sport, and so on. And more interestingly, what we have in the bottom right, we also have used LED as an artificial sun to grow our vegetables indoor, right? So that we can have our garden inside our home, right? So we really do need technologies which can reduce the energy cost of lighting, and that is why light emitting diodes, or LEDs, are so fantastic. So what we're going to do in this talk is to get right inside an LED bulb and find out what is inside, right? So this is a fairly typical LED bulb that you might be able to buy in any shop, in any hardware shop. So if you take this kind of plastic cap off, which is a diffuser, it's just there to help spread the light out, and underneath we find yellow colored square components, right? Each of that square things is an LED. So now we know that LED bulb contain multiple LEDs on a printed circuit board, or PCB, right? So let's focus on one LED, just one of that. So the yellow color is actually made of a material called a phosphor. And what a phosphor does, it absorbs light in one color and then re-emits light in another. So that's not the bit, that's not the part that actually makes light. Let us try to remove the yellow colored layer called phosphor, right? So what we can see here now is that inside the LED bulb, we have these bright blue light emitters. So our LEDs in our white light bulbs are actually giving out blue light. And then when we put the phosphor on top of it, it absorbs some of the blue and give out yellowish light. And the blue and the yellowish light just now combine, which produce something like something which looks white, right? So that's the first thing, that many white LEDs are actually giving out blue light. There are few types of packaged LEDs. These two are the most common one that we always see. We have SMD LEDs, or surface mount device. This is the same type that we saw in LED bulb earlier, right? And secondly, the normal one that you always see in your school laboratory or any electrical shop, which is called double inline, or DIL LED, right? So if we zoom in on just one of those, we've got this chip here with a sort of polymer dome over the top of it to protect it, and then contacts going out to the outside world, right? So this very tiny chip is very important. It's actually part which produce light. It is the part that actually produce light. The package LED can look different depending on the packaging design or the type of application, but the chip is what gives out light, which is what we are interested in, right? Now, let's look at what this LED structure looks like and what it's made of. This particular LED design is a blue LED chip on a patterned sapphire substrate, right? So in this chip, we have all classification of solid based on electrical conductivity, which is metal, semiconductor, and insulator. I'm sure you have learned about this in your school, right? So we have three classification of solid based on their electrical conductivity, which is metal, semiconductor, and insulator. And in this particular chip, we use all three types of solid. So at the top, we have metals, which are chromium, nickel, gold, and titanium and gold, which act as electrodes for the charge to flow inside our chip, right? And at the bottom, we have a sapphire layer, which actually acts as a substrate for the whole LED chip. And if you see in between the sapphire and also the metals, we have semiconductor material, right? This particular semiconductor material is a synthetic and man-made semiconductor called gallium nitride. It is not found in nature, and it has been made to give out blue light. Alright, so these different gallium nitride layers you can see here depicted by different colors, which are composed of slightly different from one with another. They have their specific function. Alright, so if you look at here, p-GaN is actually a p-type gallium nitride layer. Right, it is actually just a gallium nitride compound with a little bit magnesium added into it, so that it contains more positive charge carrier. While on the bottom side, we have n-GaN, n-type gallium nitride, which is actually a gallium nitride layer with silicon added to it, so that it contains more negative charge carrier. So it's opposite to the p-GaN. And we've also got MQW. MQW layer stands for multi-quantum well layer, which act as the location where the positive and negative charge carrier recombine, which the process produce efficiently, or the process efficiently produce light. Right? And this particular MQW layers is what determine the color of the light that comes out of the LED. And by tuning the indium composition within the MQW layers, we can produce light or we can produce green light, we can produce blue light, down to UV, ultraviolet emission from that LED, right? We just play around with the composition of the indium that we put inside the MQW layers. All right. The thickness of these layers are as thin as 3 nanometers. So it's very, very thin. You know, 1 nanometer is a billionth of a meter. So therefore, only can be seen using an electron microscope. And in fact, there are only a few atomic layers thick. And it is these really tiny layers of indium gallium nitride that actually gives out the light of our LED. Right? When we compare this LED to the old tungsten lamp, right? The light actually that comes out from the tungsten lamp is actually produced by flowing current to a resistor, which is the tungsten. And as the wire becomes so hot, some of the energy is converted into light as the charge move around in the wire. So that's why tungsten lamp is very inefficient, and it consumes high power because it primarily produces heat energy as opposed to producing light, right? So we have seen the structure of LED chip, right? We have seen the structure of LED chip. So now let's look at the fabrication process. We call it process flow that we use in our advanced laboratory at INO. So the process begins with LED structure, followed by ITO deposition, meta photolithography, ITO etching, MESA etching, and contact metal deposition, and finally we have this stage called and finally the P and N contact metal deposition to complete the process. Take note that the process flow is very dependent on the design and the material of the LED chip that we have planned to produce. Okay, let's go through the process one by one. So the first process is LED epitaxial wafer growth using an equipment called metal organic chemical vapor deposition, or in short MOCVD, right? Metal organic chemical vapor deposition. So the schematic on the top shows LED epitaxy structure with many layers with different colors, and at the bottom we have cake lapis from Sarawak, right? And both look very similar, right? They have layers and different colors. It is because growing this epitaxial layer in MOCVD is just like baking a layered cakes in an oven. So we mix our ingredient and we bake them at a certain temperature to get a uniform layer on a tray, right? In MOCVD, however, the ingredients are brought into the reactor in the form of gases, while heating up the tray, which we call it substrate in this process, into a certain temperature. And by doing that, we can produce high quality GaN layers, and by doing that, high quality GaN layers can be grown into a specific composition and thicknesses. Now you might say, just bake it, easy. But for cake, yeah, it is easy, but for epitaxy layer, it is very challenging and very complex process because of a number of reasons. The first is we need to use very precise monitoring system to ensure smooth, defect-free GaN layers, right? That's why the equipment is very huge. Secondly, we need to precisely control the growing process so that the thickness can be controlled up to a nanometer, which is just a few atoms thick. And thirdly, the temperature of the reactor need to be precisely controlled, as the growth process is very sensitive towards a change of temperature, even 1 degree Celsius, right? And the fourth is only ultra high purity and quality precursors will be used so that epitaxy wafer will be free of contamination and defect, right? Whenever we have contamination and defect, our device, our LED will not perform as good as what we want it to be. So if you ask me what are the types of gallium nitride that our MOCVDs can produce, so the answer is the following. We can produce gallium nitride or GaN, we can produce indium gallium nitride in GaN, aluminium gallium nitride, right? Aluminium gallium nitride or AlGaN, aluminum nitride, ALN, N-type GaN, and P-type GaN, as what we have covered earlier, right? So this is a glimpse of our MOCVD operation at INO. So what we do is we load the substrate into the reactor, we upload the recipe that we want, and the machine will do the baking until our epitaxy wafer is ready. So we have a fantastic team who are expert in managing and maintaining this equipment. So in February 2023, we managed to produce one of the most efficient white LED in the world, exceeding industry standard at 200 lumen per watt, right? Alright, so that's the first step, which is producing LED epitaxy using MOCVD. Then we move to our fabrication lab, where the subsequent processes will be performed here. Well, before we go to the next process in fabrication LEDs, let's familiarize with some processes that we do here. The first is process called deposition, right? What is deposition? Deposition is a process of adding thin layer of material on top of our gallium nitride layer. So we use equipment called E-beam, electron beam evaporator deposition to do it, right? And the second process is photolithography process. So photolithography process is a process of using light to create specific pattern on the layer using light sensitive polymer or using light sensitive polymer, which we call it photoresist, right? The third process that you need to familiarize is etching process. So etching process is a process of removing a part or area on our epitaxy wafer to form a desired shape using gases. Okay, now let's go to the next stage, which is ITO deposition. In this stage, we deposit indium tin oxide layer on top of our LED epi wafer with a thickness around 110 nanometer. Do you still remember the name of equipment that we use to deposit ITO? Yes, it is a electron beam evaporator, right? Then the next stage is to create a mesa or top hat structure on our sample using photolithography process. This is done inside a room that only have yellow light, and the reason is because the writing process using light is very sensitive towards blue and UV light. And we use equipment called maskless lithography to do the writing. After the process, this is how our sample will look like, right? So we have now added a pattern using a photoresist or PR layer. Right. So the next stage is ITO etching process. We use equipment called inductive coupled plasma reactive ion etching, or ICP-RIE. And some part of the ITO will be removed out, leaving just the PR pattern that we have transferred in the photolithography process earlier. Then we will remove the PR layer, photoresist layer, and continue to etch the epi wafer until the NGAN layer, right? And the reason of doing this is to expose the NGAN layer so that we can create an electrode on top of it, right? So that we can create an electrode on top of it. Remember, our LED should have two electrodes. One is positive, which is connected to a P-GaN layer, to the top P-GaN layer, and another one is a negative electrode, which is connected to N-GaN layer. Now, our LED begins to take shape, right? But we are not finished. We still need to add the electrodes which made of metal, right? And we do that by doing end contact deposition again using e-beam evaporator. But since we only want to deposit the metal, which is titanium aurum or titanium gold, at the N-GaN layer only, therefore we need to use photolithography again to do so. So the last stage is we need to add another metal deposition for creating another layer on both negative and positive electrodes, which we also need to perform using e-beam evaporator together with photolithography process to expose the deposition only at the area that we want. This time the electrode is composed of chromium, nickel, and gold. So actually we have another step right after we have completed N and P metal deposition, right? Metal contact deposition, and the process is called metallization. So what we do, we heat up the deposited metal contact using equipment either rapid thermal processing or RTP or furnace, alright, until a certain temperature. The difference between these two equipment is RTP provide quick heating, while furnace provide more slower but controlled heating on our sample. Right? You might ask me why we want to heat up the sample. Why we want to heat up the deposited metal contact? The reason is we have two reasons. The first is we want to improve their electrical conductivity to ensure strong and stable ohmic contact. Secondly, this process is very crucial in enhancing the interface quality between the metal and semiconductor layer, right? So we have layers of semiconductor, but on top of it we have this very small patch of metal, layer of metal, right? So therefore we need to increase the interface quality between these two different type of material. So by doing that, we can reduce contact resistance and improving overall device performance and reliability. Alright, so with that, we finally have our blue LED chip that will efficiently light up whenever we apply voltage between the two metal contacts. Right, as you can see from the left figure here, This is again the cross section of LED chip based on the process that we have covered earlier. And another figure shows the top view of the LED chip that we have produced in the fabrication process. Alright. So I hope that you all learned something during this session, and thank you for your attention, and I wish you all the best for your future. Thank you.